Okay, so what we're going to look at in this video is some related rates. Now, when we talk about related rates, we're talking about two different rates due to time or due to a third function, okay? So suppose that water is flowing into a large balloon. So this is like the idea that we're going to have surrounding this, and it's going to give us a pretty concrete example on how two rates are related to each other. So if you do have water flowing into a large balloon, then the radius and volume are both increasing, okay? So water goes in, the radius goes out, and the volume also goes out, but by a different factor. And if we know the rate at which one is increasing, we should be able to calculate the rate of increase of the other. So essentially, if we know how much the radius is increasing by over time, then we could use that to work out what the volume is going to be increasing over time, okay? So the rate at which the water is flowing in and the rate at which the radius is increasing are called related rates because one determines the other. So the water that goes in changes the radius of the balloon. So for related rates, we express one quantity as a function of the other quantity, then differentiate with respect to time, t, using the chain rule. And we've got to be careful to include the correct units when giving the final solution to problems. So some of the formulas that are necessary for related rates, and they're going to be popping up all the time, and it is required that you actually know what these are, okay? So these won't be given to you, you need to know what they are. So you've got a sphere, a cylinder, a cone, and a pyramid. So these are the big ones that you need to remember. So a sphere is 4 over 3 pi r cubed for the volume, and the area is just the derivative, 4 pi r squared. A cylinder is pi r squared h for the volume, and the area for it is 2 pi r squared plus 2 pi r h. Now a cone's volume is a third pi r squared h, okay, so the h being the height of the cone, and the area of the cone is pi r squared plus pi r l, where l is the slanted length of the cone, so that's the surface area. And finally we've got a pyramid, so a pyramid is a third the base times the height, and then the surface area is just the sum of the faces. So if it's a square pyramid, then it's it's the one square on the bottom and the 4 triangles around the outside, and from there it's all those. So there's no nice formula for that one, but it's just should be known, and we should be able to create algebraically an equation that fits our necessities. So what we're going to do is we're going to actually have a look at we're just going to jump straight in and look at two examples for this one. So starting off with example 1, a pool holds a volume of water given by V is equal to 2x plus 3x squared, where x is the depth of water. So what we're going to do is we're going to use the chain rule to find dv dt as a function of v and dv dx. Okay, so we're going to be finding the volume with respect to time as a function of the volume and the derivative with respect to x. Suppose that the flow rate is a constant 1.3 meters cubed per, I suppose that's meant to be per t, per time in the seconds. But anyway, what rate is the depth x increasing when the depth is 4 meters? And then at what rate is the radius increasing when the volume is 16 meters cubed? And suppose instead the rate is continuously being adjusted so the rate of the increase of the depth is 2 kilometers per... Oh, it's hour. That makes more sense. So it's 2 meters per hour. So find dv dt as a function of x, and what is the depth when the flow rate is 15 meters cubed per hour? Okay, well, let's start off with number 1, or part A. So we're going to use the chain rule to find dv dt. So to find dv dt, we need to do dv with respect to something times that same thing with respect to t. Now, in this case, the link in between the volume and the time is the x value, so the derivative with respect to x, and an x with respect to t. So by using this chain rule, what we can do is we can rewrite dv dt, okay, by substituting some values in and getting a formula for dv dt. So dv dt is equal to, now we need to know what dv dx is. So dv dx, I'm going to write over here, that's the derivative of this. We know it is because it's v with respect to x's, because there's x's on the inside. So that is 2x plus 3x squared go to 2 plus 6x. And so that becomes our derivative, or our dv dx, and we're going to multiply that by dx dt. Okay, so that's all it is when you were asked to find an equation, okay, or a rule. So the function is v, so we put that in there, and dv dt, or dv dx in this case, and then dx dt. Well, we don't know what dx dt is yet because we haven't been given a rate of the depth per time, but we can work what that one out is later on. So part B. Now part B is going to get a bit trickier. So part B, we are supposing that the flow rate is a constant 1.3 meters cubed per hour. So that's the rate of the volume with respect to time. So dv dt is equal to this, because the volume, meters cubed, okay, so meters cubed is a volume, with respect to time, hours. So dv dt is equal to 1.3. Okay, so this one's equal to 1.3 here. So once that one is, we worked out that one's equal to 1.3, what we're asked to actually do is, we're asked to what rate is the depth x increasing when the depth is 4 meters. So in other words, we don't know when x is equal to 4. Okay, so we want to know the rate of the depth. So we want dx dt, and we don't know what that one is. So that's what we're trying to find, dx dt. So let's substitute these values into our equation. So we get dv dt is equal to 2 plus 6x. So this is our function, okay, or our derivative function, our derivative volume. So this will find us our rate, and we do want the rate because it says in the question at what rate. Okay, so substituting this value in, so dv dt, put x is equal to 4, we're going to get 2, whoops, did this the wrong way, so it should be 2 plus 6 lots of 2, no, not 2, it should be 4, okay. Okay, we don't know what dx dt is because that's what we're going to be trying to find, but we do know that dv dt is equal to 1.3. So, actually simplifying the right-hand side, so 6 times 4 is 24, plus 2 is 26, and we're going to times that by dx dt. So this will allow us to work out what dx dt is by dividing by 26. So dx dt is equal to 1.3 divided by 26. Okay, we can actually work out what that is. 1.3 divided by 20, and that gives us 1 out of 20, or 0.05. So dx dt is increasing at a rate of 0.05 when it's 4 meters cubed. So basically, when this, I guess you'd say when the pool is filling up, so when it's filling up at a rate of 4 meters cubed per hour, then the depth of the pool is actually increasing by 0.05 meters per hour. Okay, and so this one should be meters as well. So that's part I. Okay, so part I. Now part double I says at what rate is the radius increasing? When the volume is 13. I don't know what it says radius. It probably should say volume. So at what rate is the volume or the depth increasing when the volume is 16 meters cubed? Okay, so what we want to do with this one is we're going to substitute the volume into our equation again. So what we're going to do is we're going to write when, this is part 2, when v is equal to, and I believe it was 16 meters cubed. So when this is equal to this meters cubed, so what we're going to do is we're going to substitute it back into the volume. Okay, because we want to know what the depth is of the volume. So we're going to substitute it back into this one up here. So v is equal to, and it was 2x plus 3x squared. So v is equal to 2 lots of 16 plus, we want to find what x is equal to because we know that the volume is equal to 16. So we're going to go 16 is equal to, now, 2x plus 3x squared. So factorizing this, or what I should do is I should move the 16 to the other side to get 3x squared plus 2x minus 16, because what we want to do is we want to find what the value of x is. And then once we find the value of x, we can then substitute it back into our original, or into that new derivative function, okay? Because we're asked, well, we're told that the volume is equal to 16. So once we've done this, okay, so we're looking for a number 48, okay, factors of 48 that add to give 2, or minus 48 that add to give 2. So, you know, you've got your standard 1 and 48, 2 and 24, 3 and 18, 4 and 12, 6 and 8, I believe, also make that as well. 6 times 8, just to double check, it does. And that will be the ones we're after. So 6 and 8, x, and it's going to be plus 8 minus 6. So we're going to go 0 is equal to 3x squared minus 6x plus 8x minus 16. And we're going to factorize this one. So the common factor of the 3x squared minus 6x is equal to 3x, and that gives us x minus 2 plus 8 lots of x minus 2 as well. So that means we're going to have x minus 2 and 3x plus 8. Now x must be equal to 2, or x must be equal to negative 8 on 3. Now, because we're looking for the depth when the volume is equal to 16 meters cubed, we can only have this one here, so the 2 meters here, okay, because a depth in this situation cannot be negative. So therefore, we want the x is equal to 2. So once we've done that, we're going to substitute into the other equation, so our derivative function. So dv dt is equal to, now it was the derivative of x with respect to t. So it's dx dt over here. And it was our volume derivative for our dv dt, our dv dx. So dv dx was again 2 plus 6x. 2 plus 6x, okay. What we're going to do is substitute 2 into this. We're going to 2 plus 2 lots of 2, okay, times dx dt. And we've been told about this, that's dv dt. So dv dt, I think I need to scroll back up. dv dt, is equal to 16, I'm pretty sure. Just give me 1 sec to look at my notes. I believe it should be, yeah, the 1.3 again. So we're using that 1.3 number again. So that 1.3 at the top is affecting both of these. So 1.3 is equal to 2 plus 2 times 2, so it should be 6 times dx dt. So dx, so the rate of the change in that pool is changing at a rate of 1.3 divided by 6. So dx dt, so the height of that pool is changing with respect to time when that flow is coming in at the 1.3 is 1.3 over 6. And so that one's going to be a bit bigger. It's going to be 0.217, let's say, to 3 decimal places. And that's going to give us our rate that the depth is changing again. So the dx dt. So in this case, it is meters per hour. Okay, and that's the change in that x height. Okay, of a pool. So let's come back up and we'll come to question C. So suppose instead that the rate is continuously being adjusted so that the rate of the increase of the depth is a constant at 2 meters per hour. So this time we're saying that the dx dt, because it's a constant, okay, so this is the length or the height with respect to t. So this is our dx dt this time. So that's equal to 2. So down here for C, I'm going to quickly write down dx dt is equal to 2. Okay, scrolling back up. Now find dv dt as a function of x. Okay, so what we're going to do is we're going to substitute our new dx dt into our formula. So dv, so this is part I, dv dt is equal to, now remember dv dx, well, if v is equal to, was 2x plus 3x squared, then dv dx is equal to 2 plus 6x, okay, like this. That means that dv dt, which was equal to dv dx times dx dt, okay, we can substitute these values in, so dv dt is equal to 2 plus 6x times by 2, so dv dt is equal to 4 plus 12x. And so that's the rate, or that's the rate of volume, so that's the change in volume. So the volume will be changing due to this function if we want to keep that consistent 2 meters going up per hour. So think of like this pool as like, it's some sort of like shape like this. So basically when the water gets filled up in there, okay, so it starts off pretty strong, but then it takes longer and longer and longer to fill up. So we want the height to be constantly filling up by 2 meters per hour. What we're looking at is the inflow coming in. Okay, so dv dt is equal to that, and that's our part I. Now part I says that what is the depth of the water when the flow rate is 15? So the flow rate, I'll write up here. So the flow rate here is our dv dt, because it's volume over time, and we can see that with our volume over time, so that must be our dv dt. So dv dt is equal to 15, so I'll write down here dv dt is equal to 15, but we also know that dv dt is equal to 4 plus 12x, so what we can do is we can substitute that in, and we get 15 is equal to 4 plus 12x. Now simplifying this, we're going to get 11 is equal to 12x, which means that x is equal to 11 on 12, and that's going to be our meters cubed per hour. So we've actually calculated, oh, sorry, that's a lie. We've calculated the depth at when the flow is that, so that is our depth there, so x, because and you can see that too, because it's an x value there. So what we would do is we'd say, therefore, the pool has height 11 and 12. So what's that? That's just 0.92 when the flow is, and the flow was 15 meters cubed per hour. So that's it for this video. I might do the harder of the problems in the next one, but this is our first problem. It was a bit of an easier one, and I'll see you guys in the next one.